Okay. All right, so as promised, there is another homework assignment for next week, but it's really a review, okay? Because for the first time, I actually got ahead of myself in lectures, so if you look at where we are compared to where the syllabus said we would be at this point, we're a little bit ahead. And so this is a nice opportunity to go back and review some of the things that we talked about. And if you go through these problems, I think you'll be well prepared for the exam. Now again, I don't mean to say that that's the only stuff that's going to be covered, but these are some of the things that are important. Okay? And they'll be. And just to remind you, so there's no misunderstandings, there really will be an exam here a week from today. And as I said before, you'll have the full 2 hours. Okay? Any questions about that? Okay? And again, just to remind you, we are having office hours, and I've had more customers this week than before, and more next week, but please take advantage of all of us, myself and the teaching assistants. Okay, so just to remind you, this week we covered a lot of material having to do with nuclear structure. The first part had to do with trying to understand the structure of odd A nuclei. And the basic idea there was that because of the force in the strong interaction, when I have an odd A nucleus, that means either I have an odd number of protons, number of neutrons. The even partners, let's say it's the neutrons which have the even number in this case, they all pair up to give me spin 0. And for the protons which have the odd number, then all but one of those protons pair up to give spin 0, and it's only that last or valence proton that we attribute the entire spin of the nucleus to. And so then it boils down to finding where in the shell model space that last, in this case, proton goes. Okay, so we introduced the idea of the shell model, and this came out of the notion of a central potential to which we added an LS coupling, and which split the orbitals into this funny scheme we have here. And so you had homework, and you'll have some more on trying to understand how to use that to predict the spins of at least the odd A nuclei. And in the absence of anything else, that's the best you can do to predict the spins. And you've seen, I think, in a lot of cases, you get the right answer, but not every time. And especially when you go to look at the excited states of the nuclei, the approximations break down more and more, and so you're less and less able to predict the spins. But again, in the absence of any other information, that's basically all you have to go by. Okay. And some of the independent particle shell model, as it's called, when you start moving away from the closed shells and putting more and more nucleons into a given orbital. And I don't think I showed this drawing before, but it's similar to ones we saw previously, where what you're doing is you're starting to add protons or neutrons to the F7 half shell. So this is the shell that's just above the neutron and proton magic number of 20. And as you add more and more particles to that, the level schemes that you see become more and more different, and different from what you would predict on the basis of the shell model. And the idea of what's going on here is that when you start putting 3 or 4 or 5 particles into one particular shell model orbital, and the example here is the F7 halves, but it doesn't really matter, those neutrons or protons are actually interacting with one another, okay? And that alters the excitation levels that you end up seeing. So this is another shortcoming of the shell model that doesn't really take into account the fact that these particles actually are strongly interacting and can modify the level schemes. Okay, so that's odd A nuclei. Now for even A nuclei, in some ways it's simpler, in some ways it's more complicated. First of all, we've got 2 different kinds of even A nuclei. We've got the even evens and the odd odds. Let's go to the odd odds first, because there's not a whole lot you can do except to say, okay, I've got one odd proton and one odd neutron, use the shell model to figure out the spins and pairs of them, and then add them together vectorially. Okay? And that's what this is saying, that the spin of the nucleus as a whole will be the vector sum of the neutron spin and the proton spin, and as you now know, there are many different potential outcomes from adding these 2 vectors, depending on what they are. And so the magnitude of this resulting spin j for the nucleus can range from the algebraic sum of the magnitudes of the spin of the neutron and proton down to the difference in the magnitudes. And every possible step in between in units of 1 h bar is possible. So you can't necessarily predict with 100% certainty what the spin in odd nucleus will be, you could at least give a range of potential answers. And then the empirical rule of thumb that we came up with was that when you get the potential range, you look to find the one which has the intrinsic spin of the neutron and the intrinsic spin of the proton parallel to one another. Because the deuteron, the simplest odd nucleus, likes to have the neutron and proton spin parallel. In fact, the state with the neutron and proton spin antiparallel is not bound at all. So of all these possibilities, it'll turn out only one of them will have the spins parallel. And when I say spins here, I'm talking about the intrinsic spins. And remember, these J's are sums of L and S. So you have to draw some vector diagrams and stare at them a little bit to sort that out. When we go to talk about excited states of the odd nuclei, almost all bets are off, except that since there is this range here, chances are the low-lying states of this odd nucleus will be different results from adding Jn and Jp. And there were a bunch of students in my office the other day, and we worked through a case where I think you could anything from spin 5 down to spin 0. In the case we were looking at, the state of spin 5, which was the one that had this parallel to one another, did turn out to be the ground state. But when we looked at the first excited state of the nucleus, it turned out to be the 0 plus, which is the opposite extreme. So it can give you a guideline, but it can't tell you exactly which is going to be the lowest and the level of ordering. Okay. Even evens. Okay, so even evens in their ground states are simple in that, again, because of this spin-spin interaction between all the neutrons and between all the protons, all the neutrons will pair up to give you spin 0, and all the protons will pair up to give you spin 0. And so in every single case, the ground state spin and parity of an even nucleus is 0 plus. When we go to excite the even nuclei, we saw that the level schemes that you see do not look like what you would expect if you were simply taking nucleons which were in these shell model orbitals and breaking pairs and promoting them. We went through an example of tin 130 and showed that the observed level scheme is not at all what you would predict based on the shell model orbitals that are involved. And furthermore, there were a lot of systematic trends in things like excitation energies of the first 2 plus states and the ratio of energies of the first 4 plus to the first 2 plus that indicated there was something different going on here that was a more collective kind of excitation, meaning it depended on all the nucleons in the nucleus, not just 1 or 2. And the 2 major classes of excitations for even nuclei that we talked about were vibration and rotation. And it's a semi-classical picture that in the vibration, the nucleus is doing something like this, oscillating about an intrinsically spherical shape. Whereas in the rotation, we said that quantum mechanically, it only makes sense to talk about rotation if you've got a deformed object, one which you can actually see go around. Okay, whereas if it's a sphere, you can't tell that it's rotating. And so these are the 2 major classes of excitation for the even nuclei. And for the purposes of this class and the purposes of the exams, a lot of details which we're not going to test you on. Okay. The basic idea in the vibration that we'd like you to get is that these vibrational excitations are in fact quantized, that the quantum unit we call a phonon, just a quantum of vibration like you might have heard about in solid state physics, and it turns out there are 2 different kinds of phonons. There's a so-called quantum which carries 2 units of angular momentum, and so if we have one of those in an even nucleus, the ground state being 0 plus gets excited to a 2 plus level because 2 plus 0 is 2. And when I add a second quadrupole phonon, I get 3 possible resulting outcomes of adding 2 plus 2. Now, you've seen that in principle there should be more outcomes. 0, 1, 2, 3, 4, all positive parity if nothing else were going on. It turns out, again, for sort of symmetry reasons, 1 plus, you don't need to worry about that. You can just remember that you get 0, 2, and that because the energy of each quantum is quantized, each phonon is quantized, the energy splitting here is about equal to the energy splitting here. So very qualitatively, we expect in a vibration nucleus, I'm going to see a 2 plus excited state, and then I'm going to see 2, 4 plus triplet of states at roughly twice the energy of this one. And then the other kind of vibrational phonon that's possible is what's called an octopole phonon, and it carries 3 units of angular momentum and negative parity, and it may or may not be a 3- state somewhere around the 024 triplet. But this is qualitatively the kind of energy spectrum we'd like you to be able to identify as a vibrational one. And then the other kind that we talked about was where now the idea is you have a deformed nucleus that is something which is not spherical even in its ground state, and then you begin rotating it. Okay? And you rotate it perpendicular to the symmetry axis. And again, quantum mechanically, those rotations are quantized. It can't just rotate at any old speed, if you like. And in terms of a sort of classical model of kinetic energy you associate with the rotation of a deformed object, we wrote down the quantum mechanical analog of that and found that you predict these kind of excitation energies as you go from the ground state to the first 2+ state, 4+ state, and so on. There's a parameter over here which you can't calculate. It has to do with the shape of the nucleus. But in fact, you determine it experimentally. There was a question the other day about, well, how do you know the shapes of these nuclei? It's actually from these excitation energies, you infer the moment of inertia, and you compare that to a model that allows you to predict what it would be if it were a sphere or if it were an ellipsoid with a certain deformation. And that's how you actually do it. So what you end up with then is a level scheme for a rotational nucleus, which looks qualitatively different than that for a vibrational nucleus. So now, okay, it's even, so my ground state's got a 0+, that's fine. The first excited state is 2+. So far it looks just like a vibrator. But now the next one is a single 4+ level, and the spacing here is a lot bigger than the spacing here. And I don't find another 0+ or 2+ nearby. If I keep going up, I see a 6+, again with a much larger spacing here than here. And that's the signature of a rotational nucleus. And where I ended up on Wednesday was going through this sort of algebra about the energies of these states. So calculate the energy using the formulas I just had here. So this is the prediction for what's called a rigid rotor. That means something which is rotating as a rigid body. And remember, these are really liquid, so we don't expect this to be absolutely true. But nevertheless, we can calculate then the energy of this first 2+ level is going to go as I plus 1, so 2 times 3 or 6 times this parameter, which is related to the shape of the nucleus. And then the energy of the 4+ is going to be 14 times that, and so on. What you can then do is calculate the differences in energies between these states. So we're anticipating now something we're going to start talking about next week, which is that when I have a nucleus like this, it has a ground state, which is the lowest energy state for that nucleus. But all these excited states have higher energy and higher angular momentum. And if I create a nucleus in those states, it won't stay there very long. It will decay, and most often it will decay by emitting gamma rays, photons. And it turns out, as we're going to see in a little bit, that these photons, because they don't have a huge amount of energy and because they're massless, have a hard time carrying away very much angular momentum. And so in a nucleus like this, the way these decays go is they go in steps of 2 units of h-bar. And we'll see why that is later on. But the point is, you would gamma ray, if somehow I populated that 8+ level, I would expect to see a gamma ray that goes from the 8+ level to the 6+. I wouldn't expect one from the 8+ all the way down to the ground state. That's a very difficult thing for a single photon to do. And once I got down to the 6+, I would get another gamma ray going to the 4+, and then to the 2+, and then to the ground state. And so, again, the question was, how do you determine these experimentally? One of the very powerful tools we have is to look at the energies of these gamma rays. And so the energy of the gamma ray will just be the difference between the excitation energies of these 2 states. So we can predict the energies between these states, and they're given here, and then we can predict the difference in energies between the successive gamma rays, and it turns out the differences are all the same. And so what you end up with, this is an example of a very well-studied nucleus, Prosium-152. This is not the ground state of the nucleus. This is not simply taking the ground state and making it spin faster and faster. This is a very highly excited state, which looks sort of like that diagram. It's a very deformed object where the major axis is about twice as big as the minor axis. When these were first observed, they were the first time anyone had ever seen such large deformations, and they were called super deformation because they were just so enormous. And what you see in a reaction that produces this nucleus in these very high excited states, when you look at gamma rays following the production, is each one of these is a gamma ray transition from one of those rotational states to another. And these numbers here are labeled by the spin of that particular state that's causing the transition. This state has a spin of 26 units of h bar, 28, 30, and so on. You can see they go up in steps of 2. And you can also see, I think, that the spacing between these is very regular. It's almost exactly the same. I think it's 47 keV in these cases. And that's a reflection of the fact that the moment of inertia, which is determining those energies, is staying constant. Remember, this quantity x is proportional to the moment of inertia. And the fact that these energy spacings remains the same everywhere tells you that even though this thing is whipping around really fast, it retains its shape. Okay? And that's the signature of that, this so-called picket fence gamma ray energy spectrum, where the separation energies remain constant. And the picture that we have for that is shown here. This, again, is a potential energy surface, but now, rather than plotting it as a function of the radius of the nucleus, plotted as a function of the deformation. So what we're imagining here is that you have a large nucleus, and its ground state is nearly spherical. Not quite, but nearly so. In the ground states of almost all nuclei, the deformations are small. And earlier, when we were looking at rotational excitation of nuclei starting out in their ground states, what's really going on is you've got a nucleus that's sitting down here in its ground state, and as you make it spin, you're producing excited states in this little minimum right here. So there's a minimum in the potential, and as you spin it, you're making it move to higher and higher energies, so up in this drawing. But you're still in this first minimum, the ground state deformation minimum, meaning that the deformation doesn't really change very much as I make it spin. But what was predicted theoretically and then observed experimentally is, in fact, if you are able to somehow deform the nucleus a whole lot more, initially what happens is the energy just keeps going up, meaning the nucleus doesn't like that, okay, as you try to stretch it more and more. Now, based on things we've talked about so far, does anyone have any idea why the nucleus would resist being stretched and therefore make a higher energy? So imagine I'm pulling on this nucleus and elongating it. What's happening? Yeah? The surface energy. Exactly right. Exactly right. So remember, in that semi-empirical mass formula, there's a surface term. And the reason there's that surface term is for the nucleons near the surface, they have fewer nearest neighbors than the ones in the interior, therefore less tightly bound. And so the more surface area I create, the less tightly bound the nucleus will be, and so I move up in energy there. And the sphere is the object which has the minimum surface area for a given volume. And so as soon as I start deforming it, I make the surface area larger, even for the same volume, and therefore it costs me energy. What's a little surprising is eventually you create another minimum. Okay, it turns out there's a relatively stable configuration when you've deformed it to this point of super deformation where the major axis is twice as long as the minor axis. Okay? And then in that little pocket right there, you again get rotational excitations built up on top of that. And that's what's going on in that diagram here, that these are excitations built on that shape, which is not the ground state shape of dysprosium-152. What we're going to see later on is we keep deforming the nucleus beyond something violent happens, namely nuclear fission. Okay? Eventually, I pull on it hard enough, the nucleus snaps into two. And that's again a reflection of the fact that as I increase the deformation, the energy keeps going up. It costs me energy to do that. And a lower energy state can be reached by necking the thing off into two separate pieces, and that's what nuclear fission is. Okay? All of this stuff had to do with nuclei, which we said were nearly spherical in their ground states. And the shell model, remember, assumed that empirically. So, in fact, we know from these observations that there are deformed nuclei. And this whole concept of orbital angular momentum actually only makes sense if I have a spherically symmetric system, meaning a spherically symmetric potential. So in deformed nuclei, and this isn't on your exam, this is just for your information, just to be complete about all this, that if you're talking about deformed nuclei, we really don't want to talk about L. It's not a well-defined quantum number. Total angular momentum, J, is a well-defined quantum number, and also the projection of that angular momentum onto the symmetry axis of the nucleus. So if we have this prolate spheroid, it looks like a cigar, and there's a symmetry axis along the long axis. If it's an oblate spheroid, it looks like the Earth. It's flattened at the top and bottom. Symmetry axis in the perpendicular direction. So projection of that total angular momentum on the symmetry axis is a good quantum number. And these are just pictures of what we mean by that. So here's the prolate spheroid, the thing that looks like the cigar, and the symmetry axis is along the major axis of the nucleus. And these little arrows, J1, J2, J3, are the projections of the total angular momentum onto that symmetry axis. And similarly for the oblate. Okay? And the point of all this is that you can still describe, yeah, you're owning, right? This is a mess. You thought the shell model was bad. This is a lot more complicated. The point is that these shell model states over here were calculated for zero deformation. As you start deforming the nucleus, these states split. And they split according to the total J of the state and then the projection of this J onto the symmetry axis. This is what's called a Nielsen diagram. And again, this is beyond the scope of this class. I just want to point out we do know how to deal with this. It just gets more and more complicated. And these numbers here have to do with the total J of the state and those projections. They're called Nielsen quantum numbers. And they're related to the quantum numbers you're used to from the shell model. But as you can see, it gets a lot more complicated depending on what the deformations are. But there is a model that allows us to calculate this, not from first principles. There are a lot of adjustable parameters in all this, as you can imagine. But nevertheless, there is a model that people use to calculate these things. And as a result, you can then think of a slightly more complicated situation than I talked about previously. So previously, when we were talking about rotations, we were imagining only even nuclei where the ground state has spin zero and even parity, and all I'm doing is rotating it and building up rotational excitations built on that 0 plus level. We haven't yet talked about rotations in odd A nuclei, and you might think, well, why shouldn't they happen as well? And the answer is they do. It's just that they're a bit more complicated. And so here's an example of this. This is hafnium-177. Remember the other day, the example we looked at was hafnium-180. It's sort of the poster boy for rotational nuclei. It just has a beautiful rotational excitation spectrum for an even nucleus. And this one is just 3 neutrons away from that. However, because it's an odd A nucleus, it doesn't have a 0 plus ground state. In fact, it's got a 7/2 minus ground state. And you can build rotational excitations on top of that, okay? So this is a deformed nucleus in its ground state. In this particular situation, the projection of this 7/2 minus angular momentum on the symmetry axis is 7/2 minus, so it's as aligned as it can be. And what I do is I just start rotating this nucleus, but maintaining this shape and this orientation. And I build rotational excitations on top of that single particle shell model state, okay? And you can see I get something that looks like a rotational pattern, except you're going to say, well, wait a minute, now the spacings only go 1 unit of h bar, and that's true. On the other hand, there's also another set of levels over here, which again look like a rotational band, except they're built on an excited state, okay, which has a different shape than the ground state. And so again, the point of all this is not for you to understand all this, but to get the feeling that these rotations are in fact a property of lots and lots of nuclei, not just the evens. And there is a way to understand what's going on in the odd A nuclei as well as the evens. It's just a bit more complicated. So you start with some particular state and you start making it spin. You retain the shape, just spin it faster and faster. You get rotational bands. Okay? And in a given nucleus, you might have 10 or 20 different rotational bands, all starting out with a different initial shape and a different energy. Okay. Okay, enough new stuff. So that's it in terms of what's going to be covered on the exam, okay? And what I'd like to do in the remaining 20 minutes or so. And again, I don't mean to say this is everything, but just, I know we've been covering a lot of stuff, and a lot of people coming to the office hours saying, there's a lot of stuff to cover here, and I say yes. I don't get to write the syllabus. Don't blame me. The department long ago decided what would be covered in this class, and we try our best to get through it, and it's always a bit of a struggle. So what I'd like to do is to go back to where we started from and quickly go over the basic concepts which are important. Okay, so very three things. We talk about nuclei in terms of the number of protons and neutrons in them, just nomenclature. In all the processes involving nuclear reactions, the number of neutrons and protons is fixed. Whatever you started with initially remains the same at the end. You should be able to use that idea. We don't create or destroy neutrons or protons. We do sometimes change neutrons into protons or vice versa via beta decay. And we did talk about beta decay and these mass parabolas and that kind of stuff. You should understand the basics of that. And if you don't, ask questions. I mean, this is the time to ask questions about this stuff. So just being able to identify these things, or if, you know, I didn't tell you this number, you should be able to figure it out, for example, from the other numbers. And if someone asked you a question like, what's the mass of 1 mole of K40? And I wanted to know it in grams. What's the answer? 40, okay, right? Without doing any calculations, 40, that's close enough. Okay. Angular momentum, this is the big problem, I know. It's quantum mechanical, and it's a vector. So we have to understand being able to handle that. Quantum mechanical means it's quantized. It comes in discrete units of either a half h bar or 1 h bar. Okay? If we're talking about intrinsic spin, then it's a half h bar. And if we're talking about orbital angular momentum, it's a full h bar. So the fact that it's a vector means it has a magnitude and a direction. And so if I have two different angular momenta, and it doesn't matter what caused them, okay? If they are angular momenta, then they are vectors. And if I want to compute the resulting angular momentum from summing the two, this is what I talked about a little earlier, but just to go over it, the easiest way to do it is to take these two numbers, the magnitudes of those two numbers, and add them algebraically. And that gives you the maximum possible value of this outcome. And the other thing you can do is then take the difference between these two numbers algebraically, and that gives you the minimum value. And then in steps of 1 unit of h bar, fill in everything in between. Those are the possible outcomes. And it just has to do with the relative orientations of those two vectors, J1 and J2. Okay? Now, what we're dealing with, namely the neutrons and protons and the electrons, is they have intrinsic spin. Okay? Even when they're sitting still, they're and they have intrinsic angular momentum, which is a half h bar. And when they're moving in an orbit or moving around some origin of a coordinate system, we can talk about orbital angular momentum as well. And I waved my hands and said you can think of that classically as r cross p, which is true, except that it turns out that's quantized too in integer units of h bar. And if we're talking about a neutron or proton in a given nucleus, in general, it has both orbital and intrinsic angular momentum. And the total angular momentum of that single neutron or proton then is the vector sum of L and S. Now, because S is h bar, there are only two possible results for what the J of a single neutron or proton is. It's either L plus a half algebraically or L minus a half algebraically. Okay? And the reason for that is that spin angular momentum only has two possible Z projections. It's either up or down relative to whatever axis you pick. So what that means is that for a single neutron or proton, its total angular momentum is always going to be a half integer unit of h bar. Okay, for a single proton or neutron. Because L is an integer, I add a half integer to it, I have to get a half integer. So 1 half, 3 halves, 5 halves, like that. And as a result, what that tells you right away is if I have an odd A nucleus, then the spin of that thing has to be a half integer multiple of h bar. It can't be an integer, okay? Because I've got an odd number. And similarly, for an even A nucleus, it's got to have an integer spin. 0, 1, 2, whatever, but not 7 halves, not for an even A nucleus. Okay, and just some examples. you've seen this before, but I just want to reiterate that it is really important. So for example, the simplest possible sum you could do is if I have two, so I have J1 equals a half, J2 equals a half, I just want to know what do I get when I add them, okay? So there are two possible outcomes according to the rule. So I add a half and I get 1, no big surprise. I take a half minus a half, I get 0. Those are the two possible outcomes for that. If I go to the next more complicated, or not the next, but a more complicated one, J equals 1, J1 equals 1, J2 equals 1, and I add those, okay? And I can get three possible outcomes here. I can have the two vectors pointed in the same direction, okay, and their magnitude then is just 1 plus 1, which is 2. I can have them pointed in opposite directions, and since the magnitudes are the same, the magnitudes cancel out. I get 0. But then I can have a third possibility. They could look like this, J1, J2, and therefore the magnitude of the resulting vector is still 1. It just is pointed in a different direction. So I get three different possible outcomes from adding 1 plus 1. Okay, shell model so far. We talked about the independent particle shell model. So what we're doing there is we're assuming the nuclei are spherical, and we're assuming that the total spin and parity of the nucleus as a whole can be attributable to just the last particle, the so-called valence particle. Like we talk about valence electrons in an atom, here we're talking about the valence, the outermost neutron or proton. And we're talking about odd A nuclei, so there's only one of them. And so when we start filling up the shell model, we just count up how many particles we have to account for, and where that last one goes, that's the spin and parity we read off from the diagram. Okay? So for example, if I had, let's say, a neutron, and I had some number of them between 20 and 28, so I know I'm going to have this orbital already filled, because it can only accommodate up to 20. The additional particles between 20 and 28 are going to go in here. If I have an odd number of them, I'm going to predict that the ground state spin and parity of that nucleus is going to be 7 halves, and it's going to be negative parity because the parity goes as minus 1 to the L, and this letter here is supposed to tell you what the L is. That's L equals 3. And then if I said, well, where's a good guess for where the first excited state of that nucleus would be? I've got an odd number of neutrons sitting right here. How do I excite the nucleus? Well, I take that last odd neutron and push it up to the next available shell model state. Okay? The next available shell model state is a P3 halves, so I would predict that the first excited state would most likely be a 3 halves minus. And if I wanted to get higher excited states, I would continue promoting that one odd neutron to higher and higher shell model states. And we've seen that that's a good approximation, but not 100% correct. But again, it's the best you can do, and that's all we'd ask you to do here. Going back a little further, radioactive decay. So we talked about this. You had some homework, got some more between now and Friday. If you have an assembly of radioactive nuclei, they decay, and they decay at a constant rate. And that rate is related to what we call lambda, the decay constant, and it's a unique property of a particular radioactive species. Okay, different nuclei, as we've seen, have different decay rates or half-lives. And there's a relationship between the decay rate lambda and the half-life. The decay rate is just log 2 divided by the half-life. And the half-life is the time it takes for half of whatever you started with to decay away. And again, that's an intrinsic property of the particular nucleus. And this constant really is a constant. We've seen experimentally that that's very nearly true. And so you can take that differential equation and integrate it and find the famous exponential decay law, which says that the number of this radioactive species present at time t is related to the number at t0, and it's just that number times e to the minus lambda t, where t is the difference in time between whenever you started and when now you're talking about. And remember, it doesn't matter when you start. We did that little demonstration in class with the cesium barium isotope generator and found that we got the same half-life regardless of what we called T0, okay? Because these nuclei don't know when they're born, they don't know when they're going to die, so they just die at a constant rate all the time. And so there's a related quantity which is related to the number of the species that are present. We call the activity, or the radioactivity, And it's just the decay constant times the number of nuclei present. And since n is a function of time, lambda isn't, so we just take this expression for n and plug it in here, and we see that this activity also decays exponentially. And so what we were actually measuring in that little demonstration was not the number of atoms that were present. We were measuring the activity as a function of time, but that decays exponentially too, and so it tells us what the half-life of the nucleus is. And what we were doing in class, and what you had a homework problem to do, was to take some experimental data and fit it to a functional form that looks like this. If I take the natural logarithm of the activity, I'm just taking the natural log of this thing, so I get the log of A0, the activity at t equals 0, minus lambda t. So minus lambda is the slope of that line. That's the equation of a straight line. The slope of that tells me the decay constant, and from that I can get the half-life. And I think you worked your way through the data we had taken, so you actually had experimental points here and hopefully got a half-life not too far off the known value. But that's how it's done. Oops. Okay, and I think, so for today, that's basically it. I'll finish up the review on Monday, and then we'll actually start some new stuff on gamma decay. But I'm happy to answer questions. I finished up a little earlier than I thought. If there are questions, I'm happy to do that now. If not, we'll take a break and we'll have the problem session. Yeah?
So when do you not assume that the mass of an atom is...
Okay. So in that simple-minded example I had there, the idea was if I told you that I had, X number of grams of K40, I would expect you to be able to quickly calculate how many atoms that means. Okay. On the other hand, if I said, as you're having one of these homework problems, I tell you that in a radioactive decay, there's an alpha particle that carries away 5.03 MeV. And I tell you, assume you know the mass of the parent, calculate the mass of the daughter. It's not enough to tell me it's 4 units lower than the mass of the parent. So it depends on how the question is phrased, really. Now's your chance. No? Yeah?
On the exam, we have the shell model.
Yes, yes. You don't have to memorize that. I don't remember either. I have to look it up every time.
What about like conversions?
What do you mean conversions?
Meg electron volts to joule.
Yes, you'll have all the constants you need. Yes, you don't have to write any of those down. Any numerical value that's needed for the calculation, I will give you. Okay, this isn't...
Should we like write down the binding energy equations on a cheat sheet?
So the question is about the binding energy, the semi-empirical mass formula. If there were a problem related to that, I would give you the equation. It's too complicated to memorize. Okay, at least for me. It's not a memorization class, believe it or not. Okay, so we'll give you ideas. That's what we're trying to do here. What we'd like you to be able to do is calculate based on those basic ideas. Okay?